Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to write a work energy equation, trying to take into account all energy transfers that can show up in a lot of these problems. So what we're looking at here, we've got this object which is sitting on an incline, and we're going to imagine that this object is released from rest. It accelerates down this incline, acting under the gravitational force, and also there's a frictional force because there's a coefficient of friction that we're going to use in the problem. It comes in contact with the spring and then compresses at a certain amount that we're calling x here. The spring has a spring constant k. And what we want to do is using principles of work and energy, can we calculate this value for x, the amount that spring gets compressed? So I'm going to go ahead and write a work energy equation relating position 1 to position 2. PE1 plus KE1 plus work equals PE2 plus KE2. And all we have to do now is take into account all the energy transfers we can think of. All right, so potential energies. There are two types of potential energy to consider in this problem. We've got gravitational potential energy. As this object accelerates down the incline, its gravitational potential energy is decreasing. But there's also an elastic potential energy here when the mass compresses the spring. Right. Position 1 doesn't have an elastic potential energy, but it does have a gravitational potential energy. So we need to decide where to measure that from. The lowest point in the diagram is usually a good place to measure potential energy. So I'm looking here at position 2. This is as low as this box gets here in position 2. So I'm going to go ahead and call this my gravitational datum and measure my gravitational potential energy with respect to this line. All right, so under the PE1 term, we're going to have an MGH term. Now the H, the height, I'm going to do this in green. Actually, I'll do this in red. The height is this distance here. And you'll notice that that height is opposite the 30-degree angle. And the hypotenuse of the triangle I'm going to use goes all the way to about here. So the hypotenuse here isn't just d. We also probably should include that x term. So the hypotenuse is d plus x. The height we need is here, opposite the 30-degree angle. So that's going to equal d plus x sine 30. There we go. So MGH, and the h is d plus x sine 30. And again, that gives that height right there. All right. This thing starts from rest. All right, work term. I'm going to leave a little space here and come back to that. I always like to deal with work terms last. All right, the PE2 term. So at position 2, we are at our gravitational datum. So there's no gravitational potential energy at position 2. But there is an elastic potential energy due to the fact that that spring is compressed this amount x. I tried to leave it in the picture here where the spring would be at equilibrium. Here's where the edge of it is when it's compressed. That distance is how far the spring is compressed. So we're going to have a 1/2 kx squared term for the PE2. KE2 is 0 when this is at maximum compression, at just for an instance velocity is 0. All right, the work term. So even though we're using work energy, a free body diagram is going to be handy here. Whenever, even though I'm not directly using Newton's second law right now, free bodies are very handy for evaluating work terms. So we know we're going to have the gravitational force, mg, kind of a twisted m, but that's what that was there for. All right, surface in contact. That's going to give us a normal force, which again, remember, will be perpendicular to the surface. So that's roughly perpendicular. So there's my normal. And again, there's a frictional coefficient mentioned, so I'm going to go ahead and include a frictional force. Frictional forces, remember, are tangent to the surface, and they oppose motion. So our frictional force is in this direction. And that's it. Those are the only forces that I can think of acting on that box as it accelerates down the incline. Now we're just going to take one at a time. The gravitational force does do work, but that's what this term takes into account. That is the work done by gravity as this thing moves from position 1 to position 2. So if we try to add another term, we'll be double dipping on that gravitational force. The normal force here doesn't do any work because it makes a right angle to the motion the entire time. The frictional force does do work, right? And the magnitude is going to be whatever the frictional force is times however far that force is applied. Now from here to here, that contact point is D. However, it moves an additional distance x here, so I would put D plus x just to be safe. Now in a lot of these problems, this distance x might be small compared to D. You may ignore it. I'm going to just not ignore it, and now I know I'm good. Now as far as plus or minus signs, the frictional force is up and left, the box is moving down and right. When the force and the velocity are in opposite directions, the work term is negative. So again, if you're not familiar with that, review my video about plus and minus signs on work. Right. So there's what the work energy theorem has to say about this problem. There's no velocities anywhere just because of the nature of the locations I chose. I chose position 1 when it was at rest. I chose position 2 also at rest. We could have, if we wanted to, called my position 2 maybe right before impact here with the spring and found a speed here because it would have had a kinetic energy term, but there's really no reason to given what I was after here, this position. Right. Next thing is, how do we handle this frictional force? Well, remember that the frictional force is equal to the coefficient of friction times the normal force. And again, if you're not familiar with friction and how to deal with it, I've got a video on frictional coefficients. And then the million-dollar question is this: how do we handle the normal? When you're dealing with friction, you'll almost always need the normal force, and you typically can get it by summing forces in the direction of the normal. So I'm going to go ahead and write an equation, sum of all forces. I guess I'll go ahead and just call it the normal direction, up and right positive. And I'm going to take note that this object isn't going to accelerate in this direction. If it did, it would jump right off the incline. So this sum is equal to 0. Right? So we look at our free body, and we say, all right, the normal is obviously in the direction of the normal. The mg has components in the direction of the normal, or at least a component. I'm going to go ahead and draw the vector components for mg, and I'm going to draw these in red. So the component down the incline here, mg sine theta. I'll describe where I'm getting that in just a moment. And then the component that's in the direction of the normal, or I should say in the opposite direction of the normal. That one is going to equal mg cosine theta. Now here's where I'm getting those from. The hypotenuse of this triangle is mg. This is the angle I'm calling theta. Now this is 30 degrees. That makes this one 60. And that makes this interior one here 30. Since this component is opposite the 30 degrees, its magnitude, mg sine 30. This component is adjacent to the 30 degree angle, so its magnitude, mg cosine 30. All right, so the normal we get by summing forces in the direction of the normal. Now this black force vector here that I've kind of covered up here with the red was up and to the right. That's for this term. Then there's this red vector component down and left. So we're going to have minus mg cosine 30 degrees. Minus because I've got up and right positive, and that vector component is down and left. And that's it. Those are the only forces in this free body that have a component that's along this axis. So equals 0. So the normal is equal to mg cosine 30 degrees. So I'm going to go ahead and now rewrite this equation, kind of putting everything together. So we're going to have mg times d plus x sine 30 degrees. There's our PE1 term. Minus, all right, frictional force times distance. And the frictional force is equal to the coefficient of friction times the normal. And the normal is mg cosine 30. So that's subbing this here, and then both of these here. All right, times distance to make it a work term. Equals 1/2 kx squared. Right? So here's our PE1 term. Here is the energy lost by the system via work. The loss is reflected in that minus sign as far as the system is concerned. As far as the box is concerned, that's a loss in energy. And I'll make other videos talking about where that energy went. For now, I'll just say that it's not reflected in the dynamics of the box. It's not in a potential energy term or a kinetic energy term anymore. This is the PE2 term. and there's no KE2 term because my position 2, this box is at rest. So I hope this video helps demonstrate how to write a work energy equation when you have to take gravity and frictional forces and inclines and springs all into account. Hope you enjoyed it. Have a great day.